Hello, I'm Sophia, and this is my third and final paper which I'm analysing for Compex 529. This one has three different authors, and they're describing an approach to deal with uncertainty using control theory. So the research question has a fairly simple premise. Software is uniquely uncertain among the various engineering fields, which is sort of exemplified by the need to adopt development methodologies like Agile as opposed to the more traditional methods like Waterfall. And software developers are aware of this uncertainty as we need to deal with it on a day-to-day basis. And within the context of self-adaptive systems, there's been some research on dealing with uncertainty, at least as far as the environment is concerned. But there are other types of uncertainty as well. Our hardware might have limitations, it might be inaccurate. There might be unknown interactions between our software components, and the clients themselves might not actually have a perfect understanding of the behavior they want their system to have. And in fact, that's actually quite a common uncertainty in software projects. So the research question being asked is, how can we provide guarantees about the behavior of a system given all of this inherent uncertainty in the software engineering process? And just for a little bit of extra context as to why this is still a problem, one of the things that makes this really complicated is that oftentimes our software requirements are not perfectly orthogonal. So by fulfilling one requirement, we may have a positive or negative impact on another requirement, and so on and so forth. Dealing with that cascading behavior is quite challenging. And the other issue is that there are different types of requirements. So we might have a set point requirement where we say that our system should maintain a certain value. Perhaps we want our cluster to use 80% of its available resources. We have threshold requirements in which we want a value to remain above or below some threshold. So maybe we want our error rate to always be below 2%. And finally, we have optimization requirements like reducing our spend on AWS. And in software, our adaptation problems tend to actually be a combination of all three. And current approaches only tend to deal with one type of requirement at a time. You might have a system which handles set point requirements, for instance. And the other thing is that there's nothing out there for dealing with uncertainty in the actual system requirements themselves. So this is a pretty fertile area of research, and there are a number of different research projects out there, and I have links to all of the papers for these systems in my citation document. But active forms is the main one, and the authors have actually used active forms in the evaluation for this paper, and there's also a companion paper to this one where they perform an even more in-depth comparison between SimCA and active forms. So that's the one I'll focus on in the interest of saving time, because digging into all of these would probably put me far beyond the 10-minute time limit. But active forms takes an architecture-based approach to self-adaptation. It implements a complete MAPE-K feedback loop, and that loop is guided by formal models written by users which describe the different adaptation components of the system. So the idea being presented by the authors is this brand new system called SimCA star. And the SimCA here is the name of an individual controller within the system, and the asterisk represents that it's possible to have multiple of these controllers working in tandem with each other in order to optimize multiple system requirements which we may have defined for our software. And it involves 4 phases, the first of which is called identification. And the role of identification is to try and figure out where our controllers might overlap with each other. So for instance, we might have a controller C1, and C1 is responsible for looking after the reliability of our cluster. And we have a controller C2, which is responsible for the performance of our cluster. Now, if C2 ever decides to scale our cluster up horizontally, we've actually inadvertently improved the reliability of our system, because now we have extra instances, and if one instance becomes unhealthy, fewer of our users are going to be impacted, relatively speaking, assuming that our load is well distributed throughout all of our instances. So the way SimCA identifies these interactions is by systematically feeding in every single possible combination of control signal value into the plant of the feedback loop and measuring the change in all of the output variables. And once it's done that, it spits out an alpha I coefficient for each controller and for each outcome variable. And it builds a linear model of equations which it can solve. The second two phases are responsible for producing the actual controllers, and I've sort of compressed them onto one slide because this happens. It's basically the same, one process split up into two phases. But the controllers look something like this equation. K refers to the current time step. Ui of K represents the controller output. So Ui K minus 1 refers to the previous output from the controller. EI represents the error of the controller at the previous time step. And alpha I is, of course, the coefficient we produced in the previous phase. PI represents the pole of the controller, and this is actually a user-tunable parameter and allows users to trade off between responsiveness to change versus resilience to disturbance depending on the characteristics of the underlying system. So once all of these controllers are synthesized, the actual optimization phase starts, and this is the final phase. And SimCA stays in this phase unless it needs to go back to identification in response to a requirements change. And so you can see here that the controllers all work in parallel. They get fed into the simplex component, which is responsible for combining the output and producing actuation signals for each, which will hopefully modify the measured output in the way we want it to be modified. So the advantages of this approach is that SimCA star supports theoretically arbitrarily complex requirements due to its ability to accommodate for effects between requirements when they aren't totally orthogonal. And the other big advantage is that uncertainty in system parameters can be handled as well by simply reverting back to the identification phase and synthesizing more controllers which are tuned for the new system parameters, and obviously the old controllers are replaced by these new controllers once they're produced. So when we talk about evaluation, there are two methods employed here. The first is that the authors provide a set of formal guarantees offered by their system, and then they've also done two simulations of the system in action. And so they've got two scenarios. The first is involving unmanned underwater vehicles, and the second is an IoT app. And I'll be focusing on that scenario for this evaluation section. So you can see here some graphs showing the evolution of a SimCA system and the evolution of an active form system given an identical IoT scenario. And so here we have a threshold requirement, which we're looking at, where packet loss needs to be kept below some threshold. So on the left we have graphs showcasing a scenario where packet loss needs to be below 5%, and on the right we have graphs where the packet loss needs to be kept below 2%. And we can see that in the 5% case, both of these systems behave more or less identically. There's not a huge difference between them. But on the right-hand side, we see that once the requirement becomes harder to reach, active form struggles quite a bit. There's a lot of oscillation here. It never really manages to keep it underneath the 2%, whereas SimCA is able to handle the harder requirement without too many problems. And so that shows SimCA is capable of handling quite complicated requirements, even if they're quite ambitious. It's worth noting that this experiment involves a number of different competing requirements such as power consumption, which is quite important for an IoT within the context of an IoT device. So I can't really think of a whole lot to critique about this approach. The only thing I really have to say is that I'm curious as to how long identification actually takes. The authors say that the actual optimization phase is quite speedy, but I think for certain applications the search space in order to find the alpha coefficients could be quite large, and it would be interesting to see how quickly that actually occurs. I don't think it's mentioned in the paper or anything else I researched, but aside from that, I really can't come up with a particularly great critique of this paper, to be honest. It seems pretty reasonable to me.